Quantum mechanics, also known as quantum physics, quantum theory, the wave mechanical model, and matrix mechanics, part of quantum field theory, is a fundamental theory in physics. It describes physical properties of nature on an atomic scale. Classical physics, the description of physics that existed before the theory of relativity and quantum mechanics, describes many aspects of nature at an ordinary, macroscopic scale, while quantum mechanics explains the aspects of nature at small, atomic and subatomic scales, for which classical mechanics is insufficient. Most theories in classical physics can be derived from quantum mechanics as an approximation valid at large, macroscopic scale. Quantum mechanics differs from classical physics in that energy, momentum, angular momentum, and other quantities of a bound system are restricted to discrete values, quantization. Objects have characteristics of both particles and waves, wave-particle duality, and there are limits to how accurately the value of a physical quantity can be predicted prior to its measurement. Given a complete set of initial conditions, the uncertainty principle. Quantum mechanics arose gradually from theories to explain observations, which could not be reconciled with classical physics, such as Max Planck's solution in 1900 to the blackbody radiation problem, and the correspondence between energy and frequency in Albert Einstein's 1905 paper, which explained the photoelectric effect. Early quantum theory was profoundly reconceived in the mid-1920s by Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Born and others. The first put-together interpretation of quantum mechanics is the Copenhagen interpretation. This interpretation was developed by Niels Bohr and Werner Heisenberg in Copenhagen during the 1920s. The modern theory is formulated in various specially developed mathematical formalisms. In one of them, a mathematical function, the wave function, provides information about the probability amplitude of energy, momentum, and other physical properties of a particle. Quantum mechanics has had enormous success in explaining many of the features of our universe. Quantum mechanics is often the only theory that can reveal the individual behaviors of the subatomic particles that make up all forms of matter, electrons, protons, neutrons, photons, and others. Quantum mechanics has strongly influenced string theories, candidates for a theory of everything. Quantum mechanics is also critically important for understanding how individual atoms are joined by covalent bonds to form molecules. The application of quantum mechanics to chemistry is known as quantum chemistry. Quantum mechanics can also provide quantitative insight into ionic and covalent bonding processes by explicitly showing which molecules are energetically favorable to which others, and the magnitudes of the energies involved. Furthermore, most of the calculations performed in modern computational chemistry rely on quantum mechanics. In many aspects, modern technology operates at a scale where quantum effects are significant. Important applications of quantum theory include quantum chemistry, quantum optics, quantum computing, superconducting magnets, light-emitting diodes, the optical amplifier, and the laser, the transistor, and semiconductors such as the microprocessor, medical and research imaging such as magnetic resonance imaging and electron microscopy. Explanations for many biological and physical phenomena are rooted in the nature of the chemical bond, most notably the macromolecule DNA.